Hello. In this video, I'm going to teach you about molarity and the way that chemists describe the strength of solutions. So first, here are 3 cups of salt water. Every white dot is some collection of salt particles. Maybe you notice that they're not all the same. This on the left is only a little bit salty. The one in the middle is kind of salty. And the one on the right is very salty. These descriptions, these sentences that I gave you, they're not very good, and they're not very precise. For example, how salty is not very salty? How salty is really salty? I mean, what will that taste like? Can you get a picture in your head? I mean, with 3 cups, if I wanted, for example, this one right here, if I needed that amount of salt, it would be pretty easy. I could just say, give me the middle saltiness thing, right? But what if you don't have only 3 options to choose from? What if you want to choose something in between these? So how would you describe something in between that first and second cups? Like sort of a little bit salty? Or something in between the second and third? Like almost really salty? I mean, even if you can come up with a good description of those, what about amounts in between those? Like we want to have a tool that lets us describe how strong any solution is, how much stuff is dissolved in any of it. English is not your friend here. Math is your friend, but we'll get there. So similarly, here are 3 bottles of hot sauce. Now, the reason why hot sauce burns your tongue is because there's a chemical called capsaicin in it. If you don't have a lot of capsaicin, then you're not going to be very strong. But if you do have a lot of capsaicin, you're going to be very strong. It's going to feel very hot and it's going to melt your tongue off. So for example, with these 3 hot sauces, this would be sort of spicy, this one would melt your tongue off, and the one on the right would melt your face off. So let's say you have a friend who loves spicy food. You want to get into this whole spicy food thing, you're not sold on it. So you say, give me some sort of spicy hot sauce. And what you're thinking of when you think of sort of spicy is this. That's sort of spicy. But how do you know your friend doesn't want to give you this? Because maybe that's sort of spicy to them, but it'll melt your face off. I mean, you need to be way more precise. You don't want to say, give me something sort of spicy. You want to make sure that you're getting what you want. You need a way to tell people exactly how much stuff you want in your mixture. We need a way to perfectly describe how strong of a mixture we have. So possibilities, let's brainstorm. Maybe we could just tell people how many atoms you want in there. Like maybe you could say, give me, I don't know, some hot sauce with 42 billion capsaicin atoms. Which sounds like a lot, but atoms are very tiny, it's not that much. But no, that's not going to work. And this is why. These 2 cups, they have the same number of salt atoms in them. They have the same number of salt dots. But this one on the left is going to be really salty if you take a sip, and the one on the right is not going to be very salty. Because even though they have the same number of salt particles, one of them is diluted with a lot more water. So imagine it like this. You're going to take 1 gulp of water from each of these. And in your gulp, this has a lot of salt, but this one doesn't have very much salt. Even though they have the same amount. So you don't want to describe how strong a cup of salt water is by telling me how many atoms of salts are in it. Because once again, the sizes could be different. So maybe we could just tell you how many particles are mixed in per liter. Like how many per drop, something like that. And that kind of works. So the thing is, these are going to have different amounts of salt per liter, but every little salt dot is trillions of atoms, because atoms are super tiny. We deal with billions and billions and billions and billions with them all the time. So if we did this, we would be dealing with stupidly big numbers. The numbers would be something like 4.37 quintillion particles per liter of water. And this is not a number that we want to deal with. It's too annoying to write down. I would strain my wrist. So this is where molarity comes in. When you need to count a massively high number of something, it's better to use moles instead of particles. And you remember a mole is just a group of 602 sextillion things. So for example, if you're counting how many atoms of salt were in some salt water, or how many capsaicin molecules were in some hot sauce, you wouldn't want to count individual molecules, you would want to count moles of molecules. And that gives you nice numbers. This thing on the left would be about 4 moles per liter, and the thing on the right would be about 2 moles per liter. It tells you how many particles you're going to get if you take 1 gulp. And in this case, we're making a liter-sized gulp. That's a lot, but you could use any volume of water and it would be the same. So this is the technical definition of molarity. Mathematically speaking, molarity is the number of moles of a chemical divided by the number of liters that you have. If you have a lot of a chemical, then the numerator goes up and you get a big number. But if you take a lot of chemical and you mix it into a ton of water, then the denominator is going to be really big and your number is going to get smaller. So it works the way we want it to. One last bit of terminology. If something has a molarity of like 5, there are 5 moles in every liter, then we will call it a 5 molar solution. So molarity, you know what it is mathematically, but I want you to have a picture of it in your head, what it's useful for. It's a measurement of chemical density, or the strength of a solution. For example, weak sauce hot sauce would have a low molarity of capsaicin. There's not a lot of capsaicin in every drop, or in every liter. But sudden death hot sauce, that would have a high molarity, because every drop of that hot sauce, or every liter, is going to have tons and tons and tons of capsaicin. Dangerous amounts. Finally, here's some symbols. Now, it's very common to use a capital M to represent molarity. And this is freaky to some students because people want to use the capital M for moles, but you can't do that. This is commonly used for moles, so it'll be MOL or MOLES. And then the capital L is liters, but people don't normally mix that up. These two are easy to confuse. So capital M is molarity, not the same thing as moles. I lied when I said that was the last vocab. This is the last vocab. The word concentration is sometimes used as a synonym for molarity. So for example, if somebody says that this acid has a concentration of 12, that normally means that the molarity is 12. There are 12 moles of acid in every liter of that solution. And by the way, that's really dangerous. 12 molar acid. So to summarize, molarity describes the number of chemicals per liter of a solution. It also is sometimes called the concentration. It can be mathematically described with the equation molarity is equal to the number of moles divided by the number of liters, but conceptually it's the strength of the solution, how strong it is, how salty or how spicy or how acidic. A high molarity means that something has a lot of chemicals in every drop, and a low molarity means it has only a few chemicals in every drop. If you know these, then you will have learned everything that this was supposed to teach you, and you'll be well on your way to a good grade. Hope this was helpful.